Okay, so the last example, the simple harmonic oscillator, simple harmonic motion, we sketched position, velocity, and acceleration as functions of time. And that example is physically a super important example, but it's also important because it's really the only, it's pretty much the only kind of simple example that you can do that illustrates non-constant acceleration. In general, when you want to look at systems with non-constant acceleration, you need calculus. So, as I'm sure all of you know, calculus was developed, invented by Sir Isaac Newton, and independently by Leibniz. And the reason Newton invented calculus was, of course, to understand kinematics more deeply, to understand the relationship between position, velocity, and acceleration. Velocity is the time derivative, the slope of the position versus time curve. Acceleration is the time derivative of the velocity, the slope of the velocity versus time curve. So that's calculus, derivatives. And then to go the other way, to go from acceleration to velocity, you integrate. And to go from velocity to position, you integrate again. So taking derivatives and integrating. And, Newton invented this to understand kinematics better and to form a better foundation for mechanics, for dynamics. Okay, and so it's just interesting that Newton developed this during sort of a time like we're in now, COVID time. So this was the Black Death or the Black Plague or whatever it's called in the 1600s, where he left London to go out into the country so he wouldn't catch this Black Death. And during that time, he developed calculus. So anyways, so calculus. So there's two things that we're going to do with this calculus. We're going to look at the calculus and we're going to develop the two basic kinematical formulas upon which all of kinematics is based. Okay, so the first thing that we're going to look at is the relationship between velocity and position. So velocity is the time derivative of a position versus time graph, or the slope. Okay, so we're going to proceed I'm going to draw an example on the board here, and then we're going to sort of analyze that. And the example that we're going to look at is the example we had before of the car. So here is the position of the car, as a function of time. And we started at some time t initial, and the car was at x initial. Then the car sped up, moved at a constant rate, and then slowed down and came to rest again at x final. So I'm just resketching the diagram that we had before. Okay, so this was the initial point in time and space, and this was the final point in time and space. And the graph started off with zero slope, so the initial velocity was 0, and then the car picked up speed for a while until it reached a maximum speed, and then from this point forward it coasted at that constant velocity, and then at this point the brakes were applied and the velocity steadily decreased, the slope steadily decreased to 0 again. Okay, and so that was our position versus time graph, starting with 0 slope, in the coasting phase having maximum constant slope, and ending with 0 slope. Okay, so that was our car example. Now we're going to analyze this in a little bit more generality. So when we talk about calculus, derivatives, I should just mention before we go on here, is that some of you will be familiar with calculus already, taking derivatives and maybe even integrating, and some of you might not be. I think that this lecture will be valuable to both sets of students. So for those of you who are familiar with derivatives and maybe even integrals, what this will give you is some more rigorous mathematical background to where the kinematical formulas that we use come from for constant acceleration. But we'll also derive the two general kinematical formulas based upon calculus, so you'll have a rigorous background. For those of you who are not familiar with derivatives or integrals, not familiar with the calculus, think of this as this discussion as a way for you to see the power and the beauty of the language of calculus and really motivate you to understand your calculus course that you're taking this term. Calculus is central to physics. You need to understand calculus forwards and backwards, inside out. You need to understand it like the back of your hand. Okay, so this is a great introduction to how calculus works, the notation, what it's good for, all that kind of stuff. Anyways, okay, so here we have the velocity is defined as the time derivative, the rate of change of the position versus time graph, and and that's the slope. Okay, so let me write it out a little bit more explicitly. Okay, so there's always issues with space here. So let me cram this in here. So the velocity at any instant of time, okay, so let's pick a time. Let's pick a time here, somewhere between t initial and t final, a fixed time t. And we would like to figure out what is the velocity at that instant of time. Well, the velocity at that instant of time is equal to the slope of the position versus time graph at that instant of time. So we start it here, and we go up to this point on the graph, and we're asking what is the slope of the graph at that point. And so what we do is we take a line, we're going to draw a straight line, which is tangential to that curved line at that point. Okay, and so that line looks like this. Okay, and so we are interested in what is the slope of that line passes through that point at that instant of time. And that will be the velocity at that instant of time. The slope at this point is horizontal, is 0. The slope at this point is bigger than 0, increasing, increasing, increasing. Here the slope is maximum, the velocity is maximum through here, and so on. Okay, so we need to figure out the instantaneous slope. Okay, so how do we do that? Well, so slope in general is rise over run. Okay, now here we just have a single point. And so what we imagine is taking 2 points, the time t and the time t plus a small amount dt. Okay, so we really have 2 neighboring points on that curve. Now that's sort of hard to see here, so I'm going to take this portion of the graph, that little tiny portion of the graph, which is nearly a straight line. Okay, if you make the 2 points very close together, it's nearly a straight line, and I'll blow it up to a bigger picture here. So that little tiny segment is nearly a straight line. Okay, and so this point here, the initial point at time t, is here on the graph. The point at a slightly later instant of time, t plus dt, is a little bit further along the graph up here. Okay, so what we say is the time interval from here to here is dt, and that's going to be the run. That's how far you move in the horizontal direction. That appears in the denominator here and here. Okay, and then in the numerator, we have the rise, or dx. How much does dx means change in x? How much does x change when you go from here to here along the curve? Well, it changes from here to here. So this distance here is dx. So that's the rise. It's an infinitesimal rise, infinitesimal run, and the ratio of those two will give you the slope. This divided by this gives you the slope. And this straight line here is the same slope as this line over here, the line tangent to the graph at that point. Okay, so that's the idea. So derivative, just slope, is rise over run. So dx, so d means infinitesimal change in. Infinitesimal change in some quantity. So dx means infinitesimal change in x, and dt means infinitesimal change in the time. And we take the limit as dt gets smaller and smaller and smaller, so this really becomes a straight line. Okay, great. So then now we look at this. So this is this dx divided by dt. So now what we do is we look at this relationship and we think of dx as a rise and dt as a run, and we just multiply both sides of that equation by dt. And so this equation implies that dx, the rise that happens when you go from this time to this time, the rise in the graph, dx, is equal to the instantaneous velocity at that instant of time, so the slope, times the run, dt. So this is meters per second times seconds is meters. This is the displacement, the displacement along the x-axis that happens during that small interval of time, dt. And the velocity is the rate at which that displacement is happening. Okay, great. So now we have this, and then what we do is we integrate both sides. So I'll just rewrite this equation again. So dx is equal to v at the instant of time dt. And what we do is we put an integral sign in front of both terms. And what the integral sign is, so the integral sign is a curly, sort of a stylized S. So S means sum. Okay, so the integral sign refers to sum. So what it means is to add up all of the displacements from, say, some initial position xi. These are the limits of the integral from x initial to x final. And the limits here are time. time from t initial to t final. Okay, so what we're going to do is, this is an integral, and we're going to talk a little bit about what those integrals mean. So when we say the integral of dx from x initial to x final, what that means is something like this. So starting at t initial, the position is this. When you go a little bit further in time, the position is this. A little bit further in time, the position is this. A little bit further in time, the position is this. So if you were to mark those position points along the x-axis, you'd find that it looks something like this. And so what this means is to sum all of the little changes in position as you move along this graph here, sum all of the infinitesimal changes in position from this time to this time. Oh, it went up a little bit. It went along the x-axis a little bit, this small amount. Then from this time to this time, you know, it went up a little bit more, and so on. So you add all of these infinitesimal little dx's. You add up all the little rises as you go along the curve. And so the total rise then is, adding up all those rises, is just going to be this total distance. If you add all those little dx's up, you'll get a displacement equal to the distance from here to here, x final minus x initial. So the integral of dx is just the rises, which is x final minus x initial, the net rise, the total rise. Okay, and we give this a special symbol. So we give this the symbol delta x. So there are two kinds of symbols indicating change. When you put a d in front of a variable, like dx, you mean infinitesimal change, say during an infinitesimal time interval. When you put a delta, a capital Greek letter delta, in front of the x, delta means finite change in that quantity. In this case, the finite change in position from x initial to x final, namely x final minus x initial, the total displacement, during a finite interval of time, as opposed to an infinitesimal interval of time. So learn to distinguish between d, meaning infinitesimal, and delta, meaning finite changing. Okay? So that's important. So this is the displacement. Equals the displacement. The change in the x position, final minus initial, is the displacement, okay, which can be positive or negative. Okay, so that's the left-hand side. Okay, so the left-hand side is equal to delta x, the finite displacement from x initial to x final. The right-hand side is a little bit more work to figure out what that means. So, so let's just write it down over here. The integral of v at the instant of time t dt, the integration variable here, dt here, we're integrating over time from t initial to t final. So what could this mean? Well, we have a product of the velocity at an instant of time times an infinitesimal time displacement. It's a product of two terms, and that product of two terms is summed, this script s here, from t initial to t final. So what does that mean? Let's just draw this thing graphically. So you'll remember that when the car was on this particular trajectory, where its velocity increased steadily from 0 up to the coasting velocity, then it had a constant coasting velocity for a while, and then the velocity decreased steadily linearly with time to 0 velocity at t final. So let's just redraw that picture, which we had before. So this is the velocity as a function of time for this particular car example. And what did it look like? Well, it looked something like this. This is time, this is the velocity at any instant of time. This was t initial, this was t final. And let's put 0 over here on the velocity graph. This was the initial velocity, the initial slope was 0, the final slope was 0, so the initial and final velocities are both 0. Okay, and that velocity steadily increased. Velocity is the slope of the position versus time. That velocity steadily increased until it reached this coasting velocity, and then it had that constant coasting velocity for a while, and then the velocity steadily decreased as you applied the brakes and came to rest again. So that was the velocity versus time graph. And what you're going to do to compute or to evaluate this integral, what you're going to do is you're going to divide the x-axis, the time axis, into a whole bunch of small intervals of time, dt. Okay, so the space between each one of these intervals is dt. And this is some particular, on the left edge of that little interval dt, is a particular time t. Okay, so what this says is take the velocity at that instant of time t. So at that instant of time t, what is the velocity? Well, we go up like this, and that's the velocity at that instant of time t. It's somewhere between 0 and the coasting velocity during that acceleration phase. Okay? We take that velocity, we multiply by dt. So dt is a small segment, a base here. You take the height of the curve at that point in time, you multiply by the width, dt, and what you have is a very narrow little rectangle like this. And so the height of a rectangle times its base is the area. So the area of that little rectangle. And then what it does, what the integral is asking you to do is to sum the areas of all of those little rectangles. So fill this entire graph with a whole bunch of little tiny rectangles like this. And on, up like this, and up like this. I'm not going to draw them all in, but you get the idea. You have a whole bunch of narrow vertical rectangles, and you sum. And so it's the area of this rectangle plus this one, plus this one, plus this one. Obviously, that's the total area under the velocity versus time curve from t initial to t final. Total area under that funny shaped curve. So this is the area, the total area under the v versus t curve from t initial to t final. Okay? So that's great. That's the area. And that area under this curve is equal to, that's the whole point here, is that the integral of dx, this left-hand side, is delta x, is the total displacement, x initial to x final minus x initial, delta x. The right-hand side is the area under the velocity versus time curve. So this is equal to delta x. Oops, not delta t, delta x. Okay, and so what this is saying is that the displacement of an object from some time t initial to t final is equal to the area under the velocity versus time curve from that time t initial to that time t final. Displacement equals area under velocity versus time curve. Okay? And then an important thing to introduce here is the concept of average velocity. So you can see that that the velocity is certainly not constant. The velocity starts out at 0, it increases to some maximum value, then it decreases back to 0. The velocity is clearly not constant. However, there is an average velocity. So what you do is you define the area under this curve as equal to some unknown average velocity times time delta t. This is meters per second. Average velocity times seconds is meters. Displacement, total displacement. So the question here is, just like these individual rectangles are the height of the rectangle times the base, you can also draw a rectangle here. You can say delta t. Delta t is the total time. So delta t is equal to t final minus t initial. That's the total time interval. You can think of that as the base of a bigger rectangle. And then you ask yourself the question, for that base of rectangle, what average velocity should I multiply by? The average velocity is, somewhere here. This is the average velocity. It's between 0 and the maximum coasting velocity. And so you ask yourself the question, how far up do I go? What is the average velocity such that if the car were moving not at 0 velocity, then increasing, then decreasing, if it were moving instead at a constant average velocity as time went on, what would be the displacement? Well, the displacement would be the average constant velocity in meters per second times the total time over which it was doing that. Meters per second times seconds is total displacement. Okay, and so you say, yes, what value of V average would be such that the area of this rectangle equals the area of this funny shaped curve? And clearly it's going to be halfway in between here. But okay, and so you're looking at the area of that hatched car. Okay, very good. So that's that. What else can I say? So another way to rewrite this is you can write this as the average velocity. Just sort of flip this around. Average velocity is delta x divided by delta t. So I want you to distinguish between these two equations. this is the instantaneous velocity at any instant of time, is equal to the instantaneous slope of the velocity of the position versus time curve. Okay? This is the average velocity, saying that if the car moved at that average velocity for this whole time delta t, it would cover a displacement, the same displacement delta x, from x initial to x final. So if you look at this curve here, if the car instead moved not on this position versus time curve, but this position versus time curve, then the car's velocity would be constant, and the slope of the position versus time, the slope of this constant velocity is in fact v average. Okay? You can see that the velocity starts out lower than v average, then gets bigger than v average, and then gets smaller than v average again. Okay? That's the concept of v average. So distinguish between average velocity, that's delta x finite displacement over delta t finite time interval, versus instantaneous velocity, like a derivative, okay, the instantaneous slope. All right? Very good. So let's do an example. This example will be the simplest possible example you can come up with, and that's the example of constant acceleration. Okay, so the velocity, suppose that the velocity changes linearly with the time. Okay, so here is, what we're going to do is we're going to have a simple example of this where we actually calculate the area under the curve without knowing any calculus. Okay, so this is the velocity as a function of time. Simplest possible example you can come up with is something like this. So here is 0, and here is some time t initial, here's some time t final along the time axis. And let's suppose that at time t initial, the velocity has some value, say v initial, could be positive, negative, 0. Just pick a point, v initial. And so at time t initial, the velocity is v initial. At some time t final, the velocity is v final. This v final could be above, greater than v initial, could be below, could be negative, could be 0, could be anywhere. Just pick two arbitrary points on this velocity axis. And so at time t final, the velocity is v final. Now the simplest possible situation is when we connect these 2 points with a straight line. So this says that the velocity is, as time goes on, is increasing linearly with time or decreasing or whatever. It's just a straight line. Okay? And so let's figure out the area under this curve. So this is a curve, and the area under the curve will be the area of this shape, okay, starting at 0. Okay, so let's see, how do we figure this out? So delta x is equal to the area under the velocity versus time curve. So let's figure that out. So that's area. And so that area, how should we do this? Let's just write this as the integral of v of t dt from t initial to t final. Okay, and let's work this out. So we can work this out by taking this funny shape here and splitting it into two simpler shapes. A rectangle, okay, whose width is delta t, t final minus t initial, the time interval delta t, and whose height is goes from 0 to v initial, so its height is v initial. Okay, so the area under the total curve is the area of that rectangle. Okay, so what's that? The area of a rectangle is the base times the height, so it's v initial delta t. Okay, very good. And then we want to add to that the area of this triangle. And the area of a triangle is 1/2 of the area of this rectangle here. And so it's half of the base times this height. So it's plus 1/2. The base is delta t again. Yeah, I want to write delta t on the right-hand side. Delta t. Okay, 1/2 of the base, delta t, times the height. So the distance from there to there is the distance from there to there is v final minus v initial. Which will be the change in the velocity, v final minus v initial. Now you have a v initial delta t, and you have a negative 1/2 v initial delta t. And so you end up with a half v initial delta t. So you get 1/2 v initial plus v final delta t. Okay, and now let's look at this thing. What's that? Well, if you take v initial, that number, plus v final, that number, and add them up and divide by 2, well, that's the average. So that lies right in between. This is v average. Okay, so that's just equal to v average times delta t. Okay, and so we see this relationship. Delta x is v average delta t, or v average is delta x divided by delta t. Finite displacement divided by finite displacement divided by finite time interval. All right, very good. And you can also see that this v average delta t is exactly the same thing as of the car. Suppose the car, instead of increasing its velocity from v initial to v final, suppose it moved over this time interval with that constant velocity. Okay? You can see that the area under this the area of this region, the area under a v average curve for that time interval, is exactly the same as the area under the original curve. Just take that little triangle there and stick it down there, and you can see that those areas are the same. Okay, so that's sort of a graphical picture of that. So what we get is that, just sort of to summarize here, we get the displacement delta x, a finite displacement, x final minus x initial, could be positive, negative, or 0, is equal to the average of velocity times the time interval over which that displacement happens. Okay, and now this formula, this is super important, this formula is valid in general. Okay. So this is valid whether the acceleration is constant or not. Okay, this is always valid. However, in the case where the velocity, where the acceleration is constant, meaning the velocity is a linear function of time, then we have a particular formula, a particularly simple formula for v average. Namely, v average is equal to 1/2 v initial plus v final. Okay, so this formula is valid for any acceleration, constant or not. This formula is valid only in the super special case that the acceleration is constant. So this is constant acceleration. Okay, so in introductory physics courses, you very often deal with constant acceleration because non-constant acceleration requires calculus. Except in very special cases like the harmonic oscillator that I showed you, non-constant acceleration, but you can still analyze it because you know that the answer is sines and cosines. Okay, so in general, this is true. Okay, and that's what we're going to use in this course. You know, this happens to be true in the case of constant acceleration. The only examples of constant acceleration, the most common is acceleration under gravity. That's why introductory physics courses deal so much with objects sliding down inclined planes, because the force, the force acting in the direction of motion is constant, causing constant acceleration. But this is an extremely limited set of examples. In the real world, acceleration is almost never constant. Okay, and you really have only this formula. Okay, and this formula is not valid. Okay, so I really want to emphasize that point. All right, and similarly, I think I'm going to have to erase some of the board here. I'm going to try to erase some of the board in real time here. I have this new eraser, which might sort of work. Okay, so this first part of the calculus discussion dealt with the basic definition of velocity as the instantaneous slope of the position versus time graph. So velocity is dx dt. And the second part of this, and that leads to this kinematical formula. Delta x is v average delta t. Okay? But there is also a basic definition of acceleration. Acceleration as the time rate of change of the velocity as a function of time. It's exactly the same kind of analysis, and that will lead to a second kinematical formula. And there are only two kinematical formulas. You know, you might have in your high school class, heard that there are 5 different kinematical formulas or such nonsense. There's only 2 kinematical formulas, independent kinematical formulas. Okay, so we'll talk about that in more detail. Okay. Actually, this thing works not too badly for erasing. Great. Okay, so we'll move on to the second. So the first was based upon, our first part of the discussion was based upon the definition of velocity as the time rate of change of the position versus time graph. Now we'll move on to the second part of this discussion, and that is very similarly, the acceleration as a function of time is defined as the time derivative of the velocity versus time curve, or the instantaneous slope of the velocity versus time curve. Okay, so let me sort of give you an example. And the example we're going to do is based upon the harmonic oscillator, because that's a more interesting example. So remember, for that harmonic oscillator, we had something like this. This is the velocity as a function of time. And for at least part of the oscillation back and forth, the velocity, say, started off when we're... Actually, remember, let me draw this diagram over here. Okay, so we had the wall here, and we had the spring. Let's suppose that the spring was maximally compressed at this instant of time. This is T initial. So T initial, the spring is maximally compressed, and the mass is sitting at x equals minus a. It's momentarily at rest, and then that force is going to be pushing to the right. It's going to be accelerating that mass, and later on that mass will pass through x equals 0. And then it will continue on to x equals plus a. We're interested in the time interval from here to here. Okay, so at that initial time, we have that the velocity is 0. That initial velocity is 0. So v initial equals 0. And then at the final time, the velocity increases faster and faster and faster. When the mass passes through the equilibrium position, its velocity is maximally positive. So v final is equal to positive v max. We called that before. Okay, that's at time t final. And the curve was a sinusoidal function which went up like this. Okay. So that is the velocity versus time curve of this mass when it starts momentarily at rest here and then accelerates to the right, increasing its velocity from 0 up to maximum velocity. Okay, so that's the curve. And at this point over here, when the mass is at this point, we have v is equal to 0, and the acceleration is positive a max. Maximum acceleration because spring is exerting maximum force. When the mass passes through the equilibrium position, the velocity is positive v max. Okay, so that's up here. And the acceleration is momentarily 0. Okay, the spring is in its relaxed position, neither compressed nor stretched, and so it's v is equal to v max. Okay, yeah, so it's moving fast like that. Okay, great. So we got that. And what else do we want to say? So now we want to think about the acceleration, just this definition here. So the acceleration at any instant of time is equal to the slope. So the instantaneous slope of the velocity versus time curve. So at this instant of time, we're trying to figure out what is the acceleration. Well, the acceleration is the slope of the velocity versus time curve at that instant of time. So you go up to here, that's the velocity, but we're not interested in that, we're interested in the slope. So we take a straight line which lies tangent to that point. Okay, so it looks like that. And we're interested in what is the slope of that line. And we play the same game. We take not just that time interval t. To figure out a slope, you need 2 points in time and 2 points in velocity. So you take an infinitesimally neighboring point, t plus dt, okay, and then so you have 2 points along that curve, and if we expand this, blow this diagram up, as we make dt smaller and smaller, it doesn't matter how curved that is, that little segment is going to become virtually straight. Okay, so we have a virtually straight line. This is the velocity at time t, and this is the velocity up here at time t plus dt. And so we have the same as before, we have a run of dt, and we have a rise of dv. So during a time from t to t plus dt, during that time dt, the velocity changed from this value to this value. And so the rise is that distance, dv. Okay, so great. And so a of t is equal to the slope is equal to the rise over the run. Exactly the same analysis as before, is equal to dv divided by t. Slope of that line is this divided by that. Right? Very good. And so then what we do is we take this equation, a is equal to dv dt, and we multiply both sides through, by dt. So we get dv is equal to a of t dt. And you can see that's right. Acceleration, say meters per second squared, times dt seconds is meters per second. That's the change in the velocity. Okay, that's v final minus v initial. Okay, and then what we do is we integrate, we sum over both sides. In this case, we're integrating over v, so we integrate from v initial to v final. Here we're integrating over the time, so we're integrating from t initial, the corresponding t initial and t final. Okay, and on the left-hand side, the integral of dv, the same as the integral of dx, is x final minus x initial. You add up a whole bunch of infinitesimal displacements dx to get the total displacement. Here you add up from t initial to t final all of the infinitesimal little changes in velocity. Okay, and so the total change in velocity will be v final minus v initial. So this left-hand side, this is v final minus v initial, or delta v, the finite change in the velocity from initial time to final time. So that's what is on that side. And then the integral on the right-hand side is an integral of a dt. That's the area under the acceleration versus time graph. So this is the velocity versus time graph. This is the acceleration versus time graph, corresponding to the same motion from here to here of the harmonic oscillator. So this is time t initial, this is time t final, and we can see that when the mass is at time t initial, you can see that that spring is maximally compressed. It's exerting the strongest force to the right, and so at that instant of time, the acceleration is strongest to the right. And so it's a maximum acceleration plus a max, okay, at this time. And then that spring, as that spring uncompresses and becomes relaxed at this time, at this instant of time, when the mass is passing through the equilibrium position, the spring is neither compressed nor stretched. The force is zero, the acceleration is zero. So at t final, the acceleration is zero. Okay, so we have these 2 points on the curve, and this is these 2 points are connected by 1/4 of a sinusoidal function. Okay, so it looks like that. And then the idea is what we need to do to figure out the change in velocity from here to here. In other words, starting from v initial equals 0 to v final equal positive v max, that change in velocity, v max minus 0, that change in velocity is apparently, according to some math here, calculus, is the area under the acceleration versus time curve. Okay, and so you're playing the same game. You're saying, let's take this time interval from t initial to t final. That total time interval is delta t equal t final minus t initial. You break it up into a whole bunch of little intervals of time dt, and then for every one of those little rectangles, you take the acceleration at that instant of time, that's up here, and you multiply by the width of the rectangle, that's height times width is area of that little rectangle, and then you sum over all of the rectangles that fill the area under that graph. And so that's the area under the graph. Okay, and so that's equal to, so that's equal to the area. And then you ask yourself the question, same as we did for v average here, we have an acceleration average. So we say, suppose that the acceleration were not changing as a function of time. Suppose that the force that was acting on that mass were not maximum and then decreasing. Suppose it was constant. You know, what sort of constant acceleration could you have? Say, you can call it A average. What constant average acceleration could you subject that mass to so that over the same time interval, the velocity would change by the same amount that you had before? Change in velocity is the same. And so basically you're asking yourself the question, what value of A average here would be such that when I multiply the base of a rectangle by this height of a rectangle, I get the same area. The area under that rectangle, imagining that we're moving with constant acceleration, gives you the same area under this time-changing acceleration, and hence the same change in the velocity delta v. And that's what A average is. Okay? And so that's equal to A average delta t. And yeah, I think that's about it. So very similarly to here, we can now write down, another way to write this is that the average acceleration is equal to the finite change in velocity, v final minus v initial, divided by the finite time interval, t final minus t initial. Okay, so again, I want you to compare this instantaneous acceleration, okay, is the instantaneous slope of the velocity versus time curve, whereas the average acceleration is this is infinitesimal change in velocity over infinitesimal change in time. This is the average's acceleration is finite change in velocity over corresponding finite change in time. Okay, so let's see. This formula is valid in general. So now let me take this and move over to this part of the board here and write, sort of ignore everything else. We had this result. Now we're going to write that delta V is equal to A average delta T. Okay? This is a fundamental kinematical formula. This is valid in general, whether the acceleration is constant or not. In the case that the acceleration is constant, then that acceleration, the average acceleration is equal to that constant acceleration. So constant acceleration A here, we'll label it. In the case of constant acceleration, this formula becomes delta V is equal to the average acceleration, which is just the constant acceleration, times delta T. So this formula is valid only for constant acceleration A. Okay, so I want to stress several times here that there are only two, in one-dimensional motion, there are only two, well, in general, there are only two kinematical formulas. And it's this one, and it's this one. These two kinematical formulas follow from the basic calculus definition of velocity as a function, as the instantaneous slope of position versus time. So then average velocity is just delta x divided by delta t. Average velocity is delta x divided by delta t. This is completely general, as well as this. Okay, so this is completely general. And it follows directly from the definition of the instantaneous acceleration as the instantaneous slope or time rate of change of the velocity versus time curve. So these two directly result in these two kinematical formulas, which are always valid. This kinematical formula and this kinematical formula are valid only in the super limited, super special case where the acceleration happens to be constant, which restricts you basically, and for practical problems, really just to free fall, force of gravity kind of problems. Okay? So I want you to really understand that, and I would like you to use only these two formulas. Okay? Now, it is possible from these two formulas to, in the case of constant acceleration, to derive other formulas. You know, that's where the other, the big five or whatever this is called in some textbooks, the big five kinematical formulas. But really, these are the only two kinematical formulas. You can derive other formulas by plugging one into the other and so on, in the case of constant acceleration, and derive more, but there are only two fundamental ones. Okay, so let me actually just show you how you do that. Okay, so let's leave that on the board over there. And this eraser's not too bad. Okay, so in the case when you have acceleration as constant, then, as I say, you can derive some more formulas. So let's see where those come from. I wish these boards were as easy to erase as a chalk. Okay, so I thought I could erase the board and keep going, but then my battery died. So with board erased and fresh battery, let's continue on. So we're talking a little bit about calculus here, and we showed that the basic definition of velocity as instantaneous slope of position versus time leads to this general kinematical formula, and the basic definition of acceleration as instantaneous slope of velocity versus time graph leads to this general kinematical formula. These formulas are valid under constant acceleration or not. In the super specialized case and super limited case of acceleration equals constant, Okay? In that very special case, we have the following two things happen. So first of all, in this formula number 1, V average becomes if the acceleration is constant, then the velocity is changing linearly with time, and the average is just the final the final plus the initial divided by 2. It's the midway point. So V average in that formula becomes 1/2 V initial plus V final times the time interval delta t. So we'll call this equation 1 prime. It's derived from this general formula to this specific formula when acceleration is constant. And similarly, this second formula, in the case of acceleration is constant, leads to delta v is equal to, well, what's the average acceleration when the acceleration is constant? Well, it's just that constant a, okay, times delta t. Okay? So this is formula number 2 prime. Okay? So what you can do now, given these two formulas that are valid only for constant acceleration, you can plug one into the other and so on and generate other relationships. Other formulas. So let's see. So let me just sort of give you an example here. So if we take equation 2 prime and substitute that into equation number 1, actually, we know what I'm going to do. I'm going to rewrite this one a little bit. I have something a little bit different here, which I think will be more useful. So instead of writing delta v is a delta t, we'll actually spell out delta v. Delta v is v final minus v initial, and that's equal to a delta t. Okay? So great. So now there's a v initial and a v final in this equation, and a v initial and a v final in that equation. So that allows us to substitute one into the other and so on. So let's start by substituting this guy into here. So see what happens. So then we have delta x, which is x final minus x initial, is equal to 1/2. And which one do we want to substitute? Let's substitute for v final. So that's 1/2 v initial, and then we want to add v final. Well, solving this equation for v final, taking the negative v initial to the right-hand side, v final is equal to v initial plus a delta t. Okay? And then you multiply that whole thing by delta t, and so what you get is delta x equals, you have a v initial, okay, plus another v initial in these parentheses, so you get 2 v initial divided by 2 is just 1. So this is v initial delta t, and then you have a 1/2 a delta t, so plus 1/2 a delta t squared. So when the acceleration is constant, you can substitute this guy into this guy and get this formula. Okay? So if you know, for instance, the initial velocity and the time interval, well, then you can calculate the displacement, the difference between x final and x initial. Okay, sometimes you can see this written as x final equals x initial plus v initial delta t plus 1/2 a delta t squared. Okay? However, I want to point out that you can also here, to get from here to here, we substituted in for v final. We can also substitute in for v initial. So we can say, yeah, delta x is equal to 1/2. Now, v initial. Well, let's take v initial from this equation. Solving for v initial, bringing that to the right-hand side, v initial is v final minus a delta t. So v final minus a delta t, that's v initial, and then you want to add v final plus v final, and then multiply the whole thing by delta t. And so this results in, you have a v final plus v final, that's twice v final, divided by 2 is a v final delta t, and instead of a plus, we have a minus 1/2 a delta t, delta t, delta t, delta t squared. Okay? This is the way you usually see it written. If you know v initial, that's a great little kinematical formula, valid for constant acceleration. However, if you don't know v initial but know v final, this is another equally great kinematical formula that applies for constant acceleration. So stuff like that. Or another kinematical formula that you often see comes by multiplying these two equations together. Okay, so if we take, we're taking these two equations, this one, and we're going to multiply the left-hand side. We're going to multiply, if this equals this, and that equals that, then that times that equals that times that. Okay, so we're going to say, on the left-hand side, we're going to say a delta t, okay, take that times delta x, that's equal to how should we order this? Let's put this first. That's equal to that times that. So that's V final minus V initial times 1/2 V initial plus V final times delta T. Okay, so in this formula, in these left and right hand side, you'll see there's a delta T that's common, so you can just divide out by delta T and eliminate that. Okay, and then on the right hand side here, I want you to really be, this should be like drilled into your head. A plus B times A minus B is A squared minus B squared. So on the right hand side here, we have a 1/2, and this is going to be a V final squared minus V initial squared. Okay, so you should know that, that sort of thing. So very good. And so then let's just simplify this thing. Let's bring the 2 over to the other side. So what we have is this formula, V final squared minus V initial squared on the right-hand side. Multiply both sides by 2. You get a 2A delta x. 2A times delta x. And that's another useful kinematical formula that you often come across. But it's important to understand that this kinematical formula is not independent of these two. Okay? In the case of constant acceleration, these two reduce to these sort of special cases. Okay, so you should be able to solve all problems using only these two equations, and not using this one, and not using this one, and not using this one. And I encourage you to do that. Okay? It exercises your skill at and seeing that, you know, it allows you to understand clearly where the kinematical formulas are coming from. They're coming just from the basic definitions of velocity and acceleration. But I will actually comment on this one and which is the other one? And this one. Okay, in the case of constant acceleration. So let's look at the physical meaning of these kinematical formulas. Physical meaning. Okay, so as physicists, we're always interested in the meaning of the equations that we're dealing with. What do they physically refer to? So let's take two cases, example A and example B. So let's look at this guy. Delta V is equal to A average delta T. So delta V is equal to A average delta T. Okay, or in the case of constant acceleration, it's just A times delta T. And so now what we're going to do is we're going to take, so what does this thing mean? Well, it means, you know, if there's an average acceleration, meters per second squared times time interval seconds, that'll give you the change in the velocity, you know, meters per second, change in velocity. But you might sort of recognize this, or you might get some intuition into what this formula means by multiplying both sides of the equation left and right by the mass m. Okay, so if you do that, then on the left-hand side you have m delta v, and on the right-hand side you have m a average times delta t. Now, m times delta v, if the mass is constant for the object, that's the same thing as the change in mv. That's the change in the momentum. So the left-hand side is the change in the momentum p, the x component of the momentum of the object, is equal to mass times average acceleration. Well, mass times acceleration is force, so mass times average acceleration is average force times delta t. Okay, now I wonder how many of you will recognize this. Oh, a force acting over time imparts momentum to the system. This is the momentum impulse theorem. Okay? Force times time interval is change in momentum. Just like force times displacement is change in energy, kinetic energy, force times time is change in momentum. And so we see in this the impulse. This equation is directly sort of the impulse change in momentum theorem. Where delta, this is the impulse imparted, and this is the change in momentum. Okay, as another example, let's look at, which equation do we want to look at? Oh, let's look at this one over here. Okay, so what does that thing mean? So we have V final squared minus V initial squared is equal to 2A delta x. So just like we multiplied this guy by the mass, let's multiply left and right-hand sides of that equation by 1/2 the mass. Okay, so then on the left-hand side, we're going to have 1/2 m v final squared minus 1/2 m v initial squared. That's equal to 1/2 times 2 is 1. That's equal to m a delta x. Okay, and then we look, but what's 1/2 mv squared? Well, that's the Newtonian definition of kinetic energy. So this is saying kinetic energy final minus kinetic energy initial is equal to what's mass times acceleration? Well, that's the force times delta x. And so you recognize this as change in kinetic energy. Delta K is kinetic final minus kinetic initial. Change in kinetic energy is, and I really want to emphasize that this is under constant acceleration. This is valid only for constant acceleration. It's valid only for constant force. Okay, so F constant, that constant force, times delta x. And so this you recognize as the kinetic energy equation. So work kinetic energy. So the work done by a constant force is the value of the constant force times the displacement delta x. Okay, and that work done is transfer of energy. That's the change in the kinetic energy of the object. This is the work kinetic energy theorem. Okay, and this one here, as we said, is the impulse change in momentum theorem. So that's good. It's useful to understand these kinematical formulas in terms of other relationships that you learn about. Okay, very good. So I think we're going to go through a couple of examples.